Geometric interpretation of Cartesian products. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already learned. In our previous lessons, we treated the Cartesian product primarily as an abstract algebraic concept. Essentially, we used it as a formal way to group elements from different sets into ordered pairs. While that algebraic definition is important, it is only one part of the story. Today, we are going to see how this concept moves from the realm of pure algebra into the world of geometry. You will see that the Cartesian product is actually one of the most powerful tools we have. Because it provides the very mathematical foundation for the coordinate systems we use every single day to describe positions in space. So, let's move forward and see how these abstract pairs turn into physical dimensions. 1. The two-dimensional plane, \r times r \. Now that we've established that the Cartesian product is an abstract way to group elements, let's move from the abstract to the visual. To understand this geometric interpretation, we first need to look at the building block, the set R, which represents the set of all real numbers. Think about what a real number actually is in a visual sense. Any real number can be represented as a single point on a continuous, infinite line, what we commonly call the number line. Now here is where the magic happens. When we take the Cartesian product of the set of real numbers with itself, which we denote as r cross r, we aren't just looking at a line anymore. We are creating a massive set of all possible ordered pairs, written as x, y, where both x and y are real numbers. As we will see in the next slide, this process is exactly how we transition from a simple one-dimensional line to a two-dimensional plane. Step-by-step breakdown for 2D plane. First, look at the first element of the pair, which we call x. You can think of this value as your horizontal instruction. It tells you exactly how far to move left or right along a horizontal line, which we call the x-axis. Next, we look at the second element, the y. This is your vertical instruction. It tells you how far to move up or down along a vertical line, known as the y-axis. Finally, when we combine these two specific values into an ordered pair, written as x, y, something powerful happens. By following these two precise instructions together, we are able to uniquely identify one, and only one, single point on a flat surface. This is the fundamental building block for the coordinate plane we are about to define in the next slide. Now that we have established that the Cartesian product of real numbers with itself, or r times r, gives us a collection of all possible pairs, let's break down exactly how we use one of those pairs to navigate a plane. Cartesian plane or coordinate plane. Now that we have seen how combining the x-axis and the y-axis allows us to pinpoint any specific location, we can give this entire structure a formal name. This resulting structure is known as the Cartesian plane, or sometimes the coordinate plane. It is important to realize that we aren't just talking about a few random points. We are talking about the entire infinite surface. Therefore, we can say that every single point in a two-dimensional space can be represented as an element of the set r cross r. As we will see in the next slide, this isn't just a mathematical theory. It is actually the exact same logic used by GPS technology to find your location on a map. Real-world example, GPS coordinates. Now, to make this abstract concept of the two-dimensional plane feel a bit more concrete, let's look at a real-world application that you use every single day, GPS coordinates on a digital map. Think about when you open a navigation app on your phone to find a specific shop or restaurant. To pinpoint that exact location on the Earth's surface, the system doesn't just guess. It uses two specific coordinates, latitude and longitude. Let's break this down using the mathematical language we just learned. First, we can view the longitude as our first element, which we can call x, and since longitude can be any value along a continuous line, it is an element of the set of all real numbers, written as x is an element of r. Second, we take the latitude and treat it as our second element, or our y. which is also an element of the set of all real numbers, written as y is an element of R. Finally, when we combine these two specific values, the exact location is represented as an ordered pair. X, y. This pair is a single, specific element belonging to the Cartesian product of R and R, which we denote as R cross R. So, just as we saw in the previous slides, the GPS system is essentially using the Cartesian product to turn numerical data into a precise point on a map. 2. The three-dimensional space, \r times r times r \. Now that we have a solid understanding of how the Cartesian product creates a two-dimensional plane, I want you to realize that this concept isn't limited to just 2 dimensions. We can actually extend this idea even further into higher dimensions. For instance, if we take the product of 3 sets of real numbers, which we write as r cross r, we move beyond the flat plane and create a set of all possible ordered triplets, written as x, y, and z. Instead of just having a pair of numbers, we now have a group of 3 values that allow us to describe much more complex spaces. Step-by-step breakdown for 3D space. First, we look at the first element, which we call x in a 3-dimensional context. This represents our position along the width, or what we call the x-axis. Next, we have the second element, y. Just like in the 2-dimensional plane we discussed earlier, this represents our position along the length, or the y-axis. But now we add a new dimension. The third element, z. This represents our position along the height or the depth, which we call the z-axis. When we combine all 3 of these values into what we call an ordered triplet, x, y, z, we create a unique identifier. Together, these 3 values allow us to pinpoint exactly one specific point within a 3-dimensional physical space. This is the foundation for the real-world example involving a drone's flight path that we will look at in the next slide. Now that we've seen how the Cartesian product works for a 2-dimensional plane, let's break down how we extend this logic into 3 dimensions. Real-world example, a drone's position. Now, to bring this 3-dimensional concept into the real world, let's look at a practical example involving a drone flying in the air. Imagine you are trying to describe the exact position of that drone relative to a fixed starting point on the ground. First, we look at step 1. We measure how far east or west the drone has moved. This value serves as our x-coordinate. Next, in step 2, we measure how far north or south it has traveled, which gives us our y-coordinate. Then, in step 3, we measure its altitude, or how high it is above the ground. This is our z-coordinate. Finally, in step 4, we combine all 3 measurements into an ordered triplet, x, y, z. This triplet is a single element belonging to the Cartesian product of the set of real numbers with itself 3 times, written as r times r times r. Just as we saw with the 2D plane in our previous slides, this triplet allows us to pinpoint a specific location in 3D space. As we move into our next slide, we will summarize the key takeaways from everything we have learned today. Key takeaways. First, it is important to realize the big picture. The Cartesian product is the bridge that transforms abstract, algebraic sets into tangible, spatial representations. It takes simple collections of numbers and turns them into shapes and spaces we can actually visualize. As we saw when discussing the 2-dimensional plane, the product of the set of all real numbers with itself, written as r cross r, is the mathematical way to represent a 2-dimensional plane. In this space, every single element within that set is a specific point, identified by the ordered pair, x, y. We can extend this same logic to the 3-dimensional space we just explored with the drone example. When we take the product of the real numbers 3 times, which we denote as r cross r, we are mathematically representing 3-dimensional space, where every element is a point defined by the ordered triplet x, y, z. Finally, I want to emphasize one crucial detail. The order in these ordered pairs and triplets is absolutely essential. The order is what allows us to assign a specific value to a specific dimension. For instance, the x-coordinate must always refer to the first axis, the y to the second, and so on. Without this strict order, we wouldn't be able to uniquely identify any position in space. All right, let's bring everything we've discussed today together with these key takeaways. Now, before we wrap up, let's look at a few common pitfalls to avoid when working with these concepts. Common mistakes. First, be careful not to confuse the set itself with a single point. It is a very common mistake to treat the set R cross R as if it were just one point, like x, y. Remember what we discussed in the earlier slides. The set R cross R represents the entire infinite plane. It is the collection of every possible point you can imagine. An ordered pair, such as x, y, is merely one single element or one single dot located within that vast plane. Second, never ignore the order of the elements. In geometry, the ordered part of ordered pair is absolutely critical. For instance, the point 2, 5 is not the same as the point 5, 2. If you look at the first pair, you move 2 units along the horizontal x-axis and 5 units up the vertical y-axis. But with the second pair, you move 5 units right and only 2 units up. As you can see, they land in completely different locations. Finally, try not to assume we are dealing with only discrete or separate values. When we talk about R cross R, we are working with the set of all real numbers. This includes not just integers, but all decimals and irrational numbers as well. This is a vital distinction because it is the reason why our geometric interpretation is a smooth, continuous plane, rather than just a scattered grid of isolated dots. Now, as we wrap up this lesson, I want to pause and address some common pitfalls. Even students who understand the concept of Cartesian products can sometimes stumble when applying them to geometry. I hope this clarifies the nuances of using Cartesian products in a spatial context. Keep these distinctions in mind, and you'll have a much stronger grasp of coordinate geometry.